Next speaker is Mr. Jin Zhao. He comes from the Center for Intelligent Mechatronics Research at University of Wollongong. He devotes to vehicle system dynamics and control. His topic is modeling our magnetoreological fluid dual clutch with BP neural network. So let's start his presentation.
Hello everyone, I'm Jin from University of Wollongong, Australia. And today it's my great honor to attend the ICAVP2021. And I'm going to make a presentation about some of my work which have been done in a research group. It's modeling of a magnetoreological fluid dual clutch with BP neural network. And also the co-authors are listed in the slide. They are Professor Haping Lu, Professor Donghong Ning, PhD candidate Huan Zhang, Senior Professor Wei Hua Li, and Distinguished Professor Zhongyi Zhang. And I'm going to start my presentation with the introduction. As we all know, we are facing the energy crisis, greenhouse effect, and air pollution. But EVs might be a solution for these problems we are all facing, because EV consume clean power, the electricity, which is no harm to our environment. And in order to improve the dynamic performance and the energy economy, many types of transmission systems are used for EVs, especially the dual clutch transmission, which is called DCT. The DCT is able to shift in a very short time, and it shifts smoother than manual transmission and the automatic manual transmission. And the magnetoreological fluid, which is called MR fluid, is a typical smart material. It usually is a fluid, but when there is a magnetic field applied to it, its fluid property could be dramatically changed. When there is a magnetic field applied, it will be solid-like. And the modeling objective in this paper is a dual clutch design based on the magnetoreal fluid, which combines the advantages of both DCT and MRF. It is able to transmit flexible torque rather than the rigid torque of from the conventional mechanical transmission, and it's shifts very, very fast. And in order to have better control performance, a precise mathematical model is required. So in this paper, we focused on modeling of this proposed MRFDC. Firstly, I'd like to introduce the working principle of the MRFDC. First, the clutch is used in the transmission system, as shown in the diagram. The transmission system consists of the clutch and the gearbox. The clutch mainly consists of two clutches. They are clutch 1 and clutch 2 respectively. And in detail, the MRFDC consists of a input shaft, output shaft, and two MR fluids gap, two coils, and a slip ring. The slip ring is used to input the exciting current to the coils. And because the two clutches work separately, there are two independent clutches. I'm going to introduce them respectively. First, it's the clutch 1. When there is exciting current applied to clutch 1, there will be magnetic field through the MRF1 and the coil 1 as shown in the left side picture. And the torque will be transmitted from the input shaft to the gearbox through clutch 1 at the green arrows shown in the picture listed in right side. Actually, it's the same working principle to clutch 2. When there is current applied to it, it all engages, and the torque flows at the green arrow shows in the picture listed in right side. And then I'm going to talk about the characteristics of the MRF. There are many kinds of working modes for the MRF, just like squeeze mode, damping mode, or sharing mode. In the MRF DC, the MRF fluid is supposed to work at the sharing mode. And the calculation for the output torque of the MRF DC is listed in the right side. And the output torque, or the transmission torque, or the induced torque, is the integral of the shear stress. And the shear stress is mainly consists of 2 parts. The first one is the yield stress, and the second one is decided by the dynamic viscosity and the shear rate. The shear rate indicates the shear rate is an indicator to the indicator of the speed difference between the driving disc and driven disc. And in this, in the work of in this paper, we focused on the steady state of the MRFDC. So the shear rate, also called speed difference, is neglectable because as for a clutch, there will only be speed difference between the driving disc and driven disc during the shifting process, which is transient. So in this paper, we focused on the steady state of the MRFDC. So on the condition of ideal work of the MRFDC, the driven disc and driving disc are supposed to be locked. So there will be little shear rate. And next, I'm going to talk about the structure of the BP neural network. In this paper, the modeling algorithm is selected at the BP neural network algorithm. There are 3 layers for the network, which are input layer, hidden layer, and output layer. And the input variable are selected as the input current and the first order and second order derivative of the input current. Because there is strong nonlinearity and high hysteresis in the MRFDC. And worth mentioning, the hysteresis from the magnetic field is kind of energy dissipated. So it's a kind of frequency related or changing rate related. That is, which is to say, the faster the magnetic field changes, the higher the hysteresis performs. So that's the reason why we selected the first order and second order derivative of the input current. And BP neural network is kind of the training. BP neural. The full name of the BP neural network is back propagation neural network, which is a merge layer feed-forward network, and could be trained by experiment data, and it is one of the most widely applied neural network models. In the work in this paper, the proposed model was trained by a data set acquired through experiment. The experiment data set was divided into 3 data sets. First one, training data, training set, validation set, and test set. All of the input and output data pairs are normalized and randomized, and then the network could be trained. As shown in the picture at the left side, the best performance of the network is obtained at the 53rd epoch, and the mean square error value is shown as 0.45 approximately. And the diagram in the right side shows the error distribution during the training process, which indicates that the errors are mostly within 2, and that is to say the net is well trained. The performance of the trained neural network is verified by experiment result. And firstly, let me introduce our test rig, which consists of a motor reducer, a slip ring, MFDC, a 2-speed planetary gearbox, and a torque sensor. Also, a brake is at the end of the powertrain. The system schematic is shown at the picture below. The motor is controlled by a motor controller, which is about to communicate communicate with the upper computer, and the MRFDC was excited by the power amplifier, and the power amplifier is controlled by a control board. Actually, we're using the Mariel board manufactured by National Instrument. And the exciting current could be censored, could be measured by the current sensor, and there is closed loop control. And the output torque of the MRFDC could be measured by the torque sensor, and that's how the tester rig works. And we collect data from this test rig. Here is a comparison between the real torque and the prediction torque by the proposed big neural network model. The red line indicates the real value, and the blue line indicates the prediction values. So it is shown that the model is able to precisely predict the output torque of the MIFDC. And there are 4 pictures regarding 4 frequencies to simulate different changing rate of the implied current. As I mentioned before, the magnetic hysteresis is frequency or changing rate related, and the root of the mean square error of the experiment result was carried out in the form listed in the left side. Also, the experiment result for clutch 2 is almostly the same, and the experiment results show the proposed model is able to predict the output torque values for clutch 2, and the root mean square error was listed in the table. It's all no more than 3. And in order to further verify the proposed model, there are some random or non-uniform input currents applied to both clutch 1 and clutch 2. The picture A and B the picture A and B show the input currents, and the diagram C and D show the output. The diagram C and D was a comparison between the real tested torque and the prediction torque by the proposed model. Also, the model error was shown in the table. There were no more than 3. So according to experiment result, the model is able to predict the output torque of the MRFDC very well. Also the strong non-linearity and the high hysteresis are well kept. Okay, that's all for my presentation. I'm so sorry I can't travel to Beijing and attend the meeting, attend the conference. So if you have any questions, please send me emails. And that's all for my presentation. Thank you.
It's really a regret we can't contact Mr. Zhao.